Hello. I apologize for not being present physically at for class today. Not feeling well, and I wanted though to make it up to you by doing a video concluding our discussion of applied optimization simply by doing a few more problems that are often encountered as part of any sort of standard Calculus 1 course. Remember, please, that we will be having our second midterm on Monday. That's still on. In preparation for that, on the Canvas site, you'll find all sorts of documents, a practice midterm, and all of that kind of stuff with solutions, all of that there. So please go there and take a look. Be aware also that for the Monday midterm, we will be having a review, not a review session, but like an office hours on Sunday evening. And I'm going to say Sunday at 7 p.m. It's totally optional, but for anybody that does have any last minute questions, I'm more than happy to take them then. So you'll have opportunity, and I'll send out a Zoom link and all of that because it will be done via Zoom, as you will probably have guessed. In any case, I think we can just get right to it. Let me switch scenes here. Here we go. So we want to continue doing some applied optimization problems here. Let me move the paper down like this. Okay. So here is the problem that I would like to think about today. Or one of two. I'm thinking we're going to do two because these things take a long time, especially when I'm talking through them. What is the problem? Right, I know. A right circular cone with height 8 inches and let's say base radius of 6 inches is to have a circular cylinder inscribed inside of it. Okay. So what are the dimensions, or maybe I asked, what is the volume of the maximum volume cylinder that can be inscribed? What is the volume of the maximum volume cylinder that can be inscribed? Be so inscribed, maybe is what I'll say. Okay, so let me, of course, draw or attempt to draw a picture of this situation. Here is the cylinder. No, I'm sorry, this is the cone, of course. That's a circular cone. You can't see that back edge there. Circular base. We know that, or we are told that the radius of this cylinder is 6 inches. So this distance from here to here is 6 inches. We are also told that the height of this cone is 8 inches. So we have a situation like this so far. Now inside of this cone, we are going to be inscribing a cylinder. So what does that look like? Well, first of all, there are many possible cylinders that we can insert and inscribe into the interior of this cone. Here's one. I'm trying to be a little bit general about it. So it's a circular cone, and then its base lives on the base of the cone, like this, like that. I mean, I don't know why. Okay, whatever. It doesn't matter. Okay. I'm just going to do this. I don't know why. There's something about... Okay, whatever. And then we're going to label some things about this cone. We know that a cone in particular, because we're in particular interested in volume, and maybe you should know, over here, this would be information I'd give you. I don't expect you to just know. The volume of a cylinder of height h and radius r is given by V equals, V is the first letter of the word volume, and the volume of a cylinder with height h and radius r is, so you take the area of the base, which is pi r squared, and multiply it by the height, right? So pi r squared h, that's the volume of the cylinder. And again, that way that you think about that is you have the circular base, and then you're sort of translating that a distance of h through space in the quote-unquote third dimension of space. And what you get is a resulting solid object whose volume is pi r squared h. And so in this picture, the radius is this quantity here, while the height is that quantity there, geometrically. Alrighty. Well, it's pretty clear then, I hope, where or what the objective function for this optimization problem is. Remember that you're always sort of on the hunt initially for the objective, which is the quantity in the problem that you wish to maximize or minimize. In this problem, we want to maximize volume of this cylinder that we've been describing. So we want to maximize volume, which I'll call V. And V is going to be given by a formula in terms of R and H. And guess what formula it is? It's exactly this one that I've indicated for a volume of a cylinder. It's R squared, what the heck? Pi R squared H. Like this. Apologize. Looks weird. Okay. Now, we suspect, or we expect, that there has to be some kind of constraint on the values of R and H. Obviously, without such a constraint, R and H, or a V, would be maximized just by making V, R and H as big as possible. There would not be any maximum, because you could just make the numbers bigger and bigger and bigger, and that would cause the volume to be bigger and bigger and bigger. But of course, that ignores the fact that the cylinder is inscribed in this cone. And so we need to express the fact that that the cylinder is inscribed in this cone through some kind of relationship between R and H. I'm going to say that one more time. We need to express the fact that this cylinder is inscribed in this cone through an equation, some kind of equation which is like a relationship between R and H. And for the problem, for this problem, really the challenge of this problem is to figure out what that relationship between R and H is. It's tricky to figure it out. Of course, we're given this critical information about the cone. The cone has height 8 inches and base radius 6 inches. Now, don't get all weird about it. Those are the stats, those are the specs for the cone, not for the cylinder, as you know. Don't get that just... I'm just trying to keep it straight in your head, because we're also talking about H height and R radius, but that's for the cylinder. We need to figure out some kind of relationship there. You might want to pause the video and think really hard about what a possible relationship should be between R and H. What is it? What should it look like? It should look like an equation involving only R and H and nothing else. See if you could pause the video. Well, you can pause the video. I know you know how to do that, but pause the video and give it a good 30 seconds to a minute worth of thought, maybe longer, to try to puzzle out a relationship between R and H here. Okay, so here is the idea. There are a pair of similar triangles in this picture. So similar triangles. Let me see. Do I have another color? I don't really. Wait, is this blue? That's not blue. can I do this most effectively? I don't know. Okay, I don't have another color. So I'm just going to take this this thing here. I want you to observe this triangle right here. Look at that triangle for a moment. And then look at this triangle down here. You see how there's two triangles? Actually, maybe I'll draw the picture. I'll redraw the picture with the relevant quantities. So there's this, which is supposed to represent the height of the cone. So that's 8 inches. There's this that goes across, which is 6 inches like this. And then we have a connecting line like this. And then inside of here, we have the radius of the cone sitting there. And then we go down. This is the height. Sorry, I said radius of the cone. I meant radius of the cylinder. And this is the height of the cylinder there. Okay? So we've got this set up. And the thing that I want to say, and the thing that I want us to concentrate on, I believe, is the fact that this triangle right here, and maybe I'll shade it green, is similar to the triangle that the big triangle that I've drawn here. You can see that they're both right triangles. They're both right triangles. And they share this angle right here in common. Therefore, this angle and that angle are the same. And two triangles with all the same angles are necessarily similar. Okay? So we see a pair of similar triangles here. Lovely. Now, what's nice about similar triangles is that ratios of corresponding edges in a pair of similar triangles are equal. So what I'm saying with that is that, for example, this edge, if I'm looking at the green triangle, if I take the ratio of this leg of the triangle and that edge of the triangle, that ratio of vertical to horizontal, that's equal to the ratio of the vertical to horizontal on the big triangle by virtue of the fact that they are similar triangles. So by similar triangles, I don't know, that's not English, but you hopefully get the drift of what I'm saying, trying to communicate. By similar triangles, this length over that length. Now let's think. What is this length right here? Remembering that this length here is h. Well, if this length is h, then of course this length of this sort of rectangle shape that you see there, that's also h. So this, and since this distance is 8, this distance is h, this must be 8 minus h. So the vertical side is 8 minus h. And the ratio of that to r, which is the horizontal side of the green triangle, is supposed to be equal to the ratio of the vertical leg of the big triangle, which is 8, divided by the length of the horizontal side, which is 6. Okay? So here's what I want to say. This is the constraint, or this is a relationship between h and r. To make it more explicit, we can simplify this equation. So we know, for example, 8/6 is 4/3, and I can multiply both sides by r. So I get that 8 minus h is equal to 4/3 r. That's cool. And then to figure out what r is explicitly in terms of the rest of it, I could multiply both sides by 3/4. Now, I'm going to be honest with you. I'm sort of looking back up here, and I'm realizing that if I was to solve for r in terms of h, I'd have to square that resulting expression. And I'd rather not. Whereas if I was to solve for h in terms of r, well, I don't have to square it because I can just replace that h right there by what it is in terms of r. I'm anticipating, I'm looking into the future, into my future of having to solve this problem, and I realize I have to do that. So what I'm going to do from here is in fact solve for h instead of solving for r. Okay, whatever, no big deal, right? So to do that is very easy. I can just subtract 8 from both sides and then apply a negative sign. So h is going to be equal to negative 4/3 r plus 8, I believe. If that algebra eludes you or the details are confusing, or if you ask where does the negative sign come from or where did the negative sign go, do it yourself. Figure it out. And you'll see, I believe that this is correct. It would be very embarrassing if it wasn't correct because I'm asserting that it is, but I think it is. So now we can call this our constraint. Any of these equations, because they're all equivalent to one another after all, any of these equations could work as the constraint. I'll just call this the constraint because it makes it easier to plug it in late in the next step. And then what we're going to do is make v a function of r only by replacing the h in this expression for v with this expression. Done this a number of times now. And what we learn is that v as a function of r only is pi r squared times negative 4/3 r plus 8, which of course we can simplify by distributing. So we get negative 4/3 pi r cubed plus 8 pi r squared. And hopefully that part makes sense. And this function we want to maximize. And we want to maximize it on the interval from for where r can run between 0 and 6. The minimum it could be is 0. The maximum it could be is 6. Okay? So I would suggest that at this point you pause the video and do that maximization. But in any case, I'm going to go ahead and start churning. First move that I'm going to make is try to find critical points. So I'm going to look at v prime of r, and this is a relatively elementary computation. It's negative 4 pi r squared plus 16 pi r. That's the derivative. Next thing I'm going to do is set notice, please, this is never 0. Okay, that's great. So I'm sorry, what did I just say? I said exactly what I didn't want to say. This is never undefined is what I meant to say. So we're only ever going to have critical points of the first type where we solve, where we set this thing equal to 0 and then solve. I notice that I have a common factor of 4 pi r that I can factor out. And if I do that, I get negative r plus 4, I do believe. Okay. So that leaves two critical points to think about. R equal to 0 and r equal to 4. But of course, and maybe I should have stipulated this a little bit more formally in terms of communicating my work, we just got done saying that r has to be between 0 and 6. Oh, and I apologize. Of course, r is a positive quantity, because it doesn't make sense to inscribe a cylinder of radius 0. I mean, it does to some people. It probably makes sense to you. You could probably imagine we're talking about just a sort of line segment at that point. But for the purposes of our problem here, we want to exclude that extreme value. So I guess what I'm saying is that r, maybe up here, is in the interval from 0 to 6, not including the endpoints. Okay, so in particular, this critical point corresponding to r equal to 0 is no good. We don't want it. We don't want to think about it. And so we're going to throw it out. Okay, we're going to eliminate that 0 there. We're going to ignore it is what I'm trying to say. So we only have one critical point to deal with. And now we're going to look at v double prime to use the second derivative test. Yes. And this becomes negative 8 pi r plus 16 pi, like that. And then I'm going to plug 4 in, keeping track of sign or caring about sign. So I get v double prime of 4 being negative 32 pi plus 16 pi. And it doesn't take a genius to realize I've got negative 16 pi's there, which is negative. Okay, so let's think through what that means in terms of everything that we know. We know that if we were to graph v, that because the second derivative at 4 is negative, it's concave down there. Okay, it's concave down. It looks like a frowny face, the graph. And because the derivative at 4 is 0, we know that the tangent line is horizontal. And those two facts together, concave down, tangent line horizontal, suggests that that point r equal to 4 is in fact the summit of a hill. Okay, so this says that r equal to 4 is a local maximum. Okay, great. Now, this is where we can fall back on that idea. R equal to 4 is the only local maximum of a continuous function on an open interval from 0 to 6. Therefore, r equal to 4 is, since, I'm sorry, what did I just say? Let me repeat what I said, because I feel like when I replayed it in my head just now, it didn't make sense. R equal to 4 is the only local extremum, local max or local min, on this open interval from 0 to 6. Hence, therefore, it must be a global extremum, and in this case, a global maximum. Since r equals 4 is the only local extremum on the interval from 0 to 6, it is the global extremum. And I could say whatever. It's good. Okay? And in fact, global max. Okay, great. So recalling what the problem asks, we want to find the volume of the maximum volume cylinder. So ask yourself, if we know that the global max happens when r is equal to 4, what's the volume? Well, we've got a nice function here which tells us what the volume of the inscribed cylinder is, given that we know its radius. And so all we need to do is plug r equal to 4 into this expression right here. Oh God. Okay, yeah, so v of 4. Why did I ask this question? I should have just asked for the radius, but now I have to do computation. So that's negative 4/3 pi times 4 cubed. 4 cubed is 4 times 4 times 4, which is 16 times 4, which is Nintendo 64. And then we have 8 times pi times r squared. 8 times pi times 16. Because, ew. Okay, 16. Okay, gross. So 4 times 64 is 240 plus 16, which is 256. So this is negative 256 over 3 times pi. And 16 times 8 is 80 plus 48. Oh, it's 128. And then I need to make a common denominator. Ew. How many thirds is 128? So I have to multiply 128 by 3. So that's 300 plus 60 plus 24. So is that 388? Do I believe it? No, 384. 384. That's better. Negative 256 over 3 pi plus 384 over 3 times pi. And then what's the difference? Oh, this is my least favorite arithmetic step right here, is trying to figure out what the difference between two numbers is. Add 8 and then 20 more, 28, 128? Really? Is it 128? 1, 2, 8, 8, 2, 128 over 3 pi. And don't forget units. Units are, I forgot. So the units of length here are inches, because this is America. And so this is inches cubed. That's right. Yeah, we don't use metric around here. powers of 10 are a crutch. Okay, good. Next. Next problem we should do. What should we do? So for those that are curious, I do have a document here on the Canvas site with a bunch of applied optimization problems. Let me pull that up for myself so that we can talk about it. One moment. I really should have been prepared, but I'm not. Optimization. So if you're looking at the worksheet, let's pick one of these. We've done the offshore oil rig problem. We just did the cylinder problem. Cylinder inscribed in a cone. Let's do this one. It's labeled as exercise 16.10. And we'll see if I know how to do it. I'm not sure. We'll see. A window consisting of a rectangle topped by a semicircle is to have perimeter 10 meters. I guess I'll write it. So a window consisting of a rectangle topped. Oh, good. I have 24 minutes left. Topped by a semicircle is to have perimeter. Oops. Of 10 meters. Find the radius of the semicircle if the area of the window is as large as possible. And like what's possible, you should understand, is going to be constrained by the fact that the perimeter is 10 meters. Okay. All right. So let me draw a picture of this state of affairs here. So here is a rectangle. Maybe I'll even draw across the top part. And then atop this rectangle is a semicircle. So semicircle there. All right. And now we would like to be able to write down the objective and the constraint. We have to decide, though, this is just a bare ass picture. We have to decide some quantities in this problem that are going to sort of, like the way I say it or the way I think of it is that they sort of parameterize the possible shapes of this window here. One obvious quantity that you might lean on is the radius of the semicircle, just because after all, the radius of the semicircle is the thing that we are really interested in. It's the thing that this problem is asking us to find. Find the radius which makes the area as big as possible. So let's go ahead and call the radius, let's call that R, shall we? Why R, you ask? Well, let me tell you. The reason why we chose R is because R is the first letter of the word radius. And then we're going to define maybe something else. I don't know. Maybe, well, what else do we need to know in order to understand the area of the window here? Remembering that the window is both in the semicircular part and in the rectangular part. We probably need to know the height of the rectangle. Oh, because observe with your eyeballs or with your brain balls, the bottom leg of this rectangle, also the top leg of this rectangle. The top leg of this rectangle is a diameter of this semicircle. And the diameter is, of course, twice the radius. So this length here, from between my fingers, look at it. Between my fingers, that's 2r. Therefore, this distance down here is 2r. Maybe I'll record that fact. And then what's the height? I think it's r. No, what? That's ludicrous. It's independent of the radius, right? So let's give it a name. Let's call it y. Why? Because y is the first letter of the word yite, which rhymes with height, which is important to understand. Okay. So what is the objective in this problem? Remember, the objective is not the same as the goal. Not really. When we talk about the objective function, what we're talking about is the quantity in the problem that we wish to make either as large as possible or as small as possible. In this case, of course, it's the area. And the area here we're going to denote, so we want to, maybe I'll say maximize area. And I'll call the area A, because A is the last letter of the word area. Even though that A there kind of looks like a D, it's really supposed to be an A. That looks like a crazy person's handwriting, but okay. So maximize area, which we're going to call A. Now, what is A? Well, we can just use our understandings from, basic geometry factoids to write down what A is. So first, the area of the rectangle is easy. It's 2r times y, base times height. Base times yite, I should say, right? And then we add to that the area of the semicircle. The semicircle is half of the area of a full circle. A full circle has area pi r squared. Therefore, half of that is pi over 2 times r squared. Yes. So that's area there. Okay. Now we need a constraint. And as I said at the start of the problem, when I first wrote it down, the thing preventing us from making this window as large as possible, just go off to infinity in area, is the fact that we have to we have to make the perimeter of this shape be 10 meters. Okay, so now we have the fact that 10, okay, is going to be the perimeter of this window here. The contribution from the two horizontal sides that are vertical is 2y. The contribution by the bottom is 2r. And then we have the contribution of the semicircular part here. Of course, the semicircular part is half the circumference of the full circle. The circumference of the full circle, which is another way of saying kind of the perimeter of the full circle, is 2 pi r. You learn that in high school. You might not know why. You'll learn that later in life. But then we only want half of that because it's a semicircle. So that's pi r. Cool. Now, another way of writing this is 10 is equal to 2y plus 2 plus pi r. Okay. And now I think what I'm going to do, I have a choice here. And again, I'm thinking into the future a little bit. I can either solve for y, or I could solve for or I could solve for r. I think it's preferable, at least from my perspective, to solve this for y in terms of r as opposed to r in terms of y. Why? Because then I can replace y with this with an expression in terms of r. If I had to do the other way around and substitute in r in terms of y, do you notice that it's going to get gross because I have to square the thing and put it there, and it's just like, ugh, yuck. So I'm just looking into the future there, and I'm realizing, oh, okay, let's make y, let's figure out what y is in terms of r. Oh, also, I should say, we are interested in the radius, which maximizes the area. So it would probably be therefore appropriate to write the area in terms of r. Okay, all of those things combined. So let's solve for r. This is basic algebra now. And then we divide both sides by 2. So I get y is equal to how do I want to write this? 5 minus 2 plus pi over 2 times r, I guess. Okay, cool. Now we shove this, or we substitute this into this expression for area so as to make a as a function of r only. So a of r. So I get 2r times this mess, 5 minus 2 plus pi over 2 r. And then I add to that pi over 2 times r squared. I think what I have to do now is distribute the 2r through here. And yeah, please have good hygiene. Brush your teeth for one, but then also make sure you're using parentheses. This is 10r minus, no, the 2 and the 2 there kill each other, and then the r's get married. So we have 2 plus pi times r squared. Okay, and then we have pi over 2 times r squared. I'm noticing that I have a common factor of r squared happening here. So maybe what I will do, do I care? Whatever. I'm not sure. I can't tell if it's any good to any usefulness in actually doing this. So this is what I'm going to do is distribute the minus and the r squared. So I get minus 2r squared minus pi times r squared plus pi over 2 times r squared. And then I'm looking at these two terms here. This is a full negative pizza. That's half of a pizza, positive half of a pizza. And so they're going to get married and become a negative half pizza. I don't know if that made any sense, but I'm pretty sure that's right. Pretty sure that's right. Okay. Oh, and then maybe one more move. I don't know why I'm doing this. Let's just factor out the r squared from that last bit there. Just because, I don't know. Just leave me alone. This is 2 plus pi over 2 times r squared. Okay, so that's A. Next, we're on the hunt for critical points. So we're going to take A prime. Critical points of A. Therefore, we take the derivative of A. 10 dies. This 2 comes out front by the power rule, so we get surely something is wrong here. No. Wait, surely something is wrong here. Right? Am I crazy? I feel like something very bad has happened. Okay, let me just keep going and see what happened. So I have... Oh! Okay, now I feel a lot better. Look, did you catch it? I forgot, I don't know why. I forgot the R that's right. You see where my pen is pointing? That R didn't make it down here. Okay. And I felt that disturbed me deeply, and which is why I had that little episode that you just saw. So now I take a derivative and I feel better about it. So I get 10 minus 2 times 2 plus pi over 2 times r. Okay, this feels much better to me. Notice that a prime is never undefined, but it is 0 sometimes. Let's figure out when it's 0. So first, let me just simplify this a bit. This becomes 10 minus 4 minus pi. Oh my god, I'm losing my mind. It's 4r. What am I doing this for? why am I doing it this way? I'm going to do it like this. I'm going to just distribute the 2 and then leave the minus out there. So I have 2 times 2, which is 4, and 2 times pi over 2, which is pi. Okay, that makes me feel... I'm sorry. I'm not well. Okay, there we go. Note that this is never undefined, as I think I just said. I can't remember. And then we can figure out, though, when it's 0. So we're going to solve 0 equals 10 minus 4 plus pi over r. Add 4... No. Subtract 10, divide by negative 4 plus pi, and we learn that r equals 10 divided by 4 plus pi. This is the critical point, the sole critical point for this problem. All right. And let's be clear also about what interval we're working on, what values of r we're going to allow into our consideration. We're thinking about positive values of r. Now, I know we could do a little bit better in bounding r, because this perimeter condition is going to mean that r is probably has to be smaller than infinity. However, I don't care, because if I can maximize this function on the interval from 0 to infinity, that is to say on the positive numbers, I will have also maximized it on any smaller interval consisting of only positive numbers. I guess we have to be a little bit worried that the maximum doesn't occur at some like really extreme positive value of r. But, you know, how to say, if this comes out with a normal value, with a positive value for the area, then we should expect that value of r to be a legitimate value that we can assign to the radius of this thing here. In other words, this is fine. Okay. Now let's check whether or not it's a local max or a local min. Just make that basic check there. So we're looking at a double prime of r first. That's going to be, I'm looking down here now. You see where my index finger is? Hello. You see that there? That's going to be negative 4 plus pi. And I don't know much, but I know that's negative for all r, regardless of what r is. In other words, a double prime is a constant. And in this case, it's a negative constant. Okay. That means that in particular, Euler, a double prime of 10 plus 4 plus pi, 10 over 4 plus pi, is also negative. Okay. Which implies, by the second derivative test, that r equals 10 over 4 plus pi is a local maximum. That's the conclusion that we draw from the second derivative test. But now, this is the only extremum on the positive numbers, hence it is the global maximum. Since this is the only local extremum on 0 infinity, it is a global max. And note or recall what the problem wanted. It wanted the radius, and guess what we just found? The radius. It's 10 over 4 plus pi. So the radius is equal to 10 over 4 plus pi, and we should include units on this as usual, and this is meters. Because the metric system is just superior to, I think they're called imperial units. Like, it's so stupid. Why would you have a unit of measurement which is an inch and then 12 inches in a foot? It's like so stupid. Why not just organize things around powers of 10, you know? Okay, so we did it. So those are there are two problems there that we've done. I think we've done everything in this worksheet here. Hopefully this is sufficient preparation for what I'm asking you to do in the homework. that homework is due, I think, sometime next week, okay? And you'll have an opportunity, by the way, to ask more questions because I'm having those office hours on Zoom this weekend in preparation for the midterm, which is happening on Monday, okay? So I want to conclude the video there and wish you all a nice weekend. I hope you don't get wet and it's not too wet and cold and awful out there. Like I've already said, November is, and I'm right about this. November is the worst month of the 12 months. Did I say this out loud? I can't remember, but I was feeling it in my heart, and that's the way I feel right now. This month is the worst of the 12 months. So long.